So as I was thinking about topics for today, I was just going through different parts of the Zeo code base and thinking about what we hadn't covered at one point or another. And schedules seem to be one that I don't think we've done a Zymposium session on before. So I thought that could be a fun thing for us to cover. But I think unlike sometimes we have very ambitious goals of we want to implement this hard thing and we need to fit it in. I think in this case we'll be going just a little more through what this thing is, how we use it. So I think we'll be a little bit more relaxed on pace, which one means we'll probably, I think, be close to the hour versus the hour and a half. But two, if anyone has any questions as we go along on this, or really anything else even of something else Zeo related, please feel free to jump in, and I think we can try to make this one a little bit just free flowing, organic. Yes, and I will zoom in a bit. I'm bad at doing that. My self kit always reminds me of that, so thank you for that. Okay, I think that should be significantly larger. Let me just I'll do a quick Discord check-in. I'll probably have to do a little bit more of those just because I don't have a partner crying here. Okay, so what I thought we would talk about today is this schedule data type in Zeo. And maybe actually I could start out, I'm going to try to do a little mini poll here. Let's see. So yeah, maybe just if you're in the Discord, just give a little thumbs up or thumbs down on if you've used this data type before, and I can just calibrate a little bit based on that. So it looks like right now got about half and half, which is great. So good. So hopefully we can do a little bit of an introduction, and then we can also get into a little bit more serious stuff. So I always find it's helpful when we're doing these things to have a little bit of context of why does this thing exist? What motivated someone to create this thing? And so the origin of this was, if you think about when Zeo was being developed, this was even before Zeo 1. There was this Zeo thing, and you can imagine people came along and they said, well, I want to retry something. And we said, okay, well, that's great. We'll have a little retry method, and maybe it'll take how many times you want to retry it. And then it'll just give you back this thing. And we could even imagine how we would implement that we'd basically run it, and then we would catch the error. And if it failed, we would just run it again, and we'd decrease this n by 1, and we would do that. And so that kind of made sense. And then someone came along and they said, well, that's great, but I don't want to just retry it immediately. I want to retry it with some delay. I want to retry it every 10 seconds. So maybe, I don't remember exactly what we originally called it, but maybe we say, okay, well, fine. You've got your delay, that's some duration. And probably here you still have some concept of this, how many times you want to retry it, because you probably don't want to retry it forever, but you want to retry it with some delay. So we say, fine, okay, we can implement this. And then someone comes along and they say, well, I want to do a delay, but I don't want my delay to be linear. I want to do a exponential backoff. So we're okay, we'll do retry, delay, exponential. And maybe this will take an int, and then it'll take, look at Copilot's even knowing what to do here. So it'll take some initial delay, and then it'll take some factor of how much it should, what the exponential factor is, which would probably typically be 2.0. So we could say, okay, that makes sense. But then someone comes along and they say, well, I want to do a delay for a fixed duration for this amount of time. I want to do that 10 times. And then after that, I want to do it with a exponential delay. And maybe you can kind of put these together of first you'll do this and then you'll do this, but that kind of quickly gets to probably not actually be what you want. Because if I do something like I do Zeo let's say dot retry delay 10 seconds, and then I try to retry delay exponential that. So I think if you look at this for a minute, you realize this doesn't actually do what you want to do, because this thing is going to retry 10 times for 10 seconds each. But then when this thing retries, it's going to retry this whole thing. So you're going to like do the 10 times for 10 seconds, then you're going to have a little bit of delay here, then you do another 10 times for 10 seconds. So like this isn't going to work. So like if you really wanted to do this, you do like retry linear and then exponential. And then, I mean, we'll have like a whole bunch of things here. We have like linear delay, and then I guess this would be like linear repetitions, and then we would have like, oops, oh, sorry. And then we would basically need all of these parameters. And you can see this thing is getting to be a big mess here. We have like all these different operators, and basically anytime anyone wants to do something, we need a completely different operator here. And so this is kind of, I think, the first thing that led to this idea of, okay, we need a different solution for this, right? This idea that just each of these things are going to be their own operators doesn't actually scale for us. Like if maybe everyone had like really simple needs of like all they ever wanted to do was like retry with a fixed delay a certain number of times, then like maybe this would work. But the reality is like there are all sorts of people who want to retry on all sorts of different schedules. And we can't have like a separate operator to do each of these retries. And at least the way this is set up right now, where these are just like their own methods on Zeo, it doesn't give us any way for us to put these together. And the other thing that was missing a little bit from this was, or maybe the other thing that was inspiring us that there was something we need to do here, was all of these things deal with retrying. And so conceptually, retrying, we could say that means if there is a failure, then do it again and see if it is a success. So in addition to all these, there were like another set of things that people wanted to do. That sometimes they said that they wanted to repeat something. And so this would mean, don't worry, like in retry, if it's successful, I'm done, right? If it's successful, I don't do it anymore. Versus repeating is in a way the opposite. Like typically if it fails, then we've just failed, we're done. But if it succeeds, then we want to do it again, right? Maybe we want to send a heartbeat signal every 10 seconds or every millisecond, or we want to do it this many times. And we essentially can have pretty similar operators here of like, okay, someone wants to repeat a certain number of times, but maybe they don't just want to repeat a certain number of times. Maybe they want to repeat with a certain delay. Maybe they want to repeat with a exponential delay. And so you can see here, like if we go down this road of just these being operators, pretty quickly, like I think these like repeat variants could probably become like half of the like Zeo API of just like the number of methods on Zeo that are like covering every possible way that we could want to repeat or retry. And we wouldn't even then be covering every possible way. We would just be covering kind of the common ways that we came up with. And we'd probably have a very like common problem that like every month or so, someone's going to come along on GitHub and be like, I want to do this particular form of weird retrying or repeating that isn't covered by your operators. Can you make a new operator for me? And it would just kind of be a losing proposition. So when we've got this like situation where there are just like too many variants for us and like we feel like we're getting overwhelmed by that, a lot of the times that's a clue that there's another data type that's hiding here. And so before we even get to code, we could think conceptually, there's some concept of a retry strategy. And if we had a retry strategy, then we might actually be able to delete almost all of these. So like in the very, let's to like start to like play with code, we could say, maybe we have something we call a retry strategy. And maybe then when we repeat based on a, or let's not even get to the repeating yet. Let's just focus on the retrying. So then maybe if I retry here, I don't retry a certain number of times, but I retry based on a retry strategy. And then this retry strategy could have different things of, have like linear, or let's say, well, maybe I'll call it like number of times just initially. And this is going to be a retry strategy. And I could have, and so in this world, then I could start to take these operators away. And hopefully I can get to the world where everything is just a retry strategy. And then, and maybe this actually isn't a retry strategy. Maybe let me kind of keep going incrementally, and we could call this like a retry repeat strategy. And we'll come up with a better name for it in a minute. But so if I did that, then potentially this repeat could also take this retry repeat strategy. And I could get down from all of these different operators to essentially these two different operators on Zeo. And then what I could start to do potentially is have ways of combining these different strategies. So for example, we might think conceptually this number of times is a strategy that wants to do it that many times. And this delay, we have to think a little bit about the semantics, but we might say that this delay strategy is a strategy that wants to recur with this delay, just is always willing to recur with this delay. And so then that could mean that if I want to do something like delay n times, let me make this like a def. That this could just be something like number of times and delay duration. And if we could really do that, this would, oops. This would now let us get to that composable API that we were missing before, where if we had the right primitive constructors for this retry repeat strategy, and we had the right operators for combining them, then you could define any strategy you wanted to. You could combine as complex strategies as you wanted to, and that would all kind of take place as part of this nice mini domain specific language for repeating and retrying. And so this retry repeat strategy is a really ugly name, but it's a better name could be a schedule. So you could call it a schedule for how you want to repeat or retry. Oops. And so that's basically what a schedule is. So we could say a schedule is a description of a strategy for repeating or retrying something. Does that make sense to everyone? Let me just do a little check in on the Discord here. Okay. Yeah, please jump in and just say like, yes, this makes sense, or no, that was going too fast, or I don't understand this part of it, because I want to make sure that everyone's getting something out of this. Okay, perfect. Okay, awesome. So this like conceptually makes things a lot nicer, but it pushes the work onto us a little bit to say, well, what exactly is this schedule thing? We've kind of said a schedule. I mean, if we kind of sketch out here, just based on this interface, we've said a schedule has enough information to tell, basically to tell the Zeo runtime here, to tell us when and how many times to repeat or retry something, right? That's kind of one property that's implied by what we have here. Another one that's kind of interesting is there's an implication here that a schedule can describe both a strategy for retrying something and a strategy for repeating it. And so we'll need to think a little bit about like, what does that mean? That this, what this implies so far is that I could do Zeo dot repeat schedule dot delay n times 10 1 second. And I could also do Zeo dot retry. And so that's going to have some implications for what this schedule data type is going to be, because it's got to be able to solve both of these problems. And then there's also this implication that schedule is composable, right? That it has as operators like this and one we came up with that let us build more complex schedules from simple ones. Because if all we did was we moved things onto this schedule object, but we still had to have constructors on the schedule for every individual type of schedule that one might ever have, then we haven't really solved the problem. We've just kind of moved it from the Zeo trait to the schedule companion object. So we need some way to define these schedules so that we can build more complex ones from simpler ones. And so these are kind of the key design constraints for the schedule data type. And it actually went through a good number of iterations between different versions before Zeo 1.0 and then between Zeo 1.0 and Zeo 2.0, there were some changes as well. But let me see if I can, maybe if I can click through for us here to the current implementation, and we can walk through it a little bit and then we can play with it. So let me try to do schedule dot. Okay. All right, so we're looking at the source code for Zeo right now. And you'll see the schedule has 3 type parameters. And so maybe first let's just think about these type parameters, and let's spend a minute on these. So when we've got a schedule, we have a schedule that has an environment type, what's called this in type, and what's called an out type. So let's spend a minute on what each of these mean. So I think the environment is maybe the most obvious. And the environment just means the schedule may itself use some services in deciding when to repeat or to retry. So far, the schedules that we've looked at have been pretty simple in a way of like they've either just wanted to occur at some interval of time durations or have wanted to just recur some number of times. But we can imagine we might have schedules that maybe they're going to use some third party or some service that we've defined to help them decide whether or not they want to continue. Right? Maybe they're going to like look in some file system and see if like there's a signal that like they should keep going or not. So the environment is gives them the capability to use some type of services in the implementation of these schedules. I think if you look at the schedules that are in Zeo itself, in Zeo 1.0, the only services they would use would be some schedules would use the clock service, obviously, because they would want to do scheduling of things at certain time intervals. And so the clock would provide that functionality. And then in some cases, they would use the random service because in some cases you want to like apply like a random jitter to a schedule so that like if you have a bunch of things that are supposed to occur like at 9 a.m. on Monday, maybe you don't actually want to do every one of those things exactly at 9 a.m. Maybe you want to do it like between 60 seconds before and 60 seconds after. So like you don't like generate a whole bunch of requests at the exact same time. But I think as we've talked about before in Zeo 2, both those random and clock services got removed from the environment because they're part of just those lower level default services that I think we learned like don't actually make as much sense to represent in the environment versus higher level services like your Kafka service or your persistent service or something. And I think this was maybe a good example of that. And so in Zeo itself, if we look at a bunch of these different constructors of schedules, we'll see that they don't actually generally use the environment type themselves. So like, let me, so like this schedule, let's find a good simple schedule here. So this schedule is going to repeat with a fixed delay. And we can see it doesn't use any environment type. So first one's the environment type. I think maybe the takeaway you can have from this is like if you ever needed a schedule that used some other service you've defined, that's something you could definitely do. But I think if you're just using the existing schedules, that type is always going to be any. The second type here is this input type. And this really comes up when we start to think about this concept here of wanting the schedule to work for both retrying and repeating. And in particular, where we want to look at some other schedules that are maybe a little bit more complicated than this. So when we looked at these schedules here, one of the things that we might notice about them, if we kind of thought about it a little bit, is that none of them actually care what the essentially what the input is to them. So like in the case of the retry schedule, all of our retries were just like retry 10 times, retry every second, retry with an exponential back off. But the reality is that we might want what we do for our retries to depend on what type of error we got, right? If we're trying to access some remote service and we got an error that our password's invalid, then there's probably not a point in retrying at all, right? I mean, if it's invalid, like someone's got to go manually reset it or something. It's not like trying it 2 seconds from now is going to make it go through when it didn't go through before. And in fact, it's probably going to like make things worse because it's going to trigger like a all these like security things of like, oh, there are multiple password failures or what have you. Versus like if it's a like, well, the connection like timed out or something, then maybe we want to like retry it right away, or we want to retry it quite quickly because then maybe we think that's a very like transient error. And so we might actually want to be able to have what we're doing, our decision about whether we continue, depend on the error we're getting. And in the case of repeating, we could have a similar thing of like, so far we were just like repeat 10 times, repeat every second, but we might want to repeat until a condition becomes true. Right, we might want to like, maybe we have a lot of like algorithms where we say, maybe we're doing a numerical approximation, right? Repeat until the approximation is within this tolerance. And that's something that we could do. And so what those imply is that the schedule needs to have this input type, which represents the type of information that it consumes. And so in the case of retrying something, a schedule consumes errors. In the case of repeating something, a schedule consumes success values. And so there's actually, if we want to like geek out a minute, there's some nice symmetry here, right? Of we see that retrying and repeating are actually like kind of two sides of the same coin. That what it means to retry something is to apply a schedule to the error channel, and what it means to repeat something is to apply a schedule to the value channel. So that's kind of cool, at least if you're geeky like me, you think it's cool. And then the final, and so if we look at this and we go back to the actual schedule in Zeo, we'll see that a lot of schedules also have any as their input type. So like this schedule here is recurring with a fixed delay, and it doesn't care what the input is. It's going to recur with that delay. So it can accept any input. But we have some others, like let's look at, there's one called recur while equals. And so this is a schedule that only wants to continue as long as the value that it gets as the input is equal to this value here. And so you'll see here, this schedule doesn't require any environment, but it does require, it only consumes values that are of this type A. So if I do like recur while equals no such element exception, that's a schedule that only takes no such element exceptions, or only takes throwables as inputs. And so that would make, in that case, that schedule would probably make sense to apply for retrying. It wouldn't make sense to apply for repeating in those cases, because the success value is probably not going to be a throwable unless we were doing something very unusual. And then the final type parameter here is this out value. And so this just represents some kind of summary value that the schedule can produce. And so a lot of times the schedule will either not produce a meaningful value, or maybe it'll just pass through the value that was originally given to it. Right, in a lot of our original examples, we had this assumption that we just want the original value back. But this out type can also be useful because maybe we want the schedule to keep track of how many times it's run, or what the last delay is between when it was run. And what we'll see when we get into some of these operators, like this and operator or some of the others, is that this can also be useful for composing these schedules. Because let's say this out type represents like how long the delay was since it ran last. If we wanted to double the delay, well, that's going to give us the information to do that. So those are the three type parameters of a schedule. I want to show you one other thing here so you're not thrown off by it. So you'll notice here, if you look at a lot of these constructors, like let me go back to that, maybe that fixed one. So you'll notice here, there's this, like here, I think this now hopefully will make sense, where we say, okay, this fixed schedule is a schedule that doesn't require any environment. It doesn't take any inputs, or well, rather, it will accept. It's happy to accept any inputs at all, and it's going to return a long. And if we look at the documentation, we see that in this case, this long represents the number of repetitions of the schedule so far. So, okay, that hopefully makes sense so far. But then when we look at this, you might say, hey, Adam, you've kind of have not been fully honest with me here, because I see the schedule here, but I see this other weird type here, schedule.withState. And I see this really weird option of a pair of longs and then another long. And I'm like, what the heck is going on here? And so I'll give you two answers to this. So the first is, I think you're not going to have to worry about that much. Like, this is kind of designed to just be like pass through for you. So unless you're doing something specific with it at all, you can just forget this entirely. You can just essentially type this as a schedule. I can't change the source code here, but you can say that this is a schedule any long. So you can just type it that way and forget this whole weird state thing. That being said, the reason it exists is because one of the design goals that we had for schedule as we did more work on it was we wanted schedules to be serializable, and we wanted you to be able to deserialize them and to preserve type information. And so as we get into the implementation of schedule a little bit, what we're going to see is that a schedule might maintain some internal state, right? So if we think about like our exponential backoff schedule here, I think we deleted the exponential backoff schedule. Let's go to it here. So if we think about the exponential backoff schedule, so this is going to do something like delay 1 second, 2 seconds, 4 seconds, 8 seconds, 16 seconds. It's going to need to keep track of some internal state to know the next time it delays is supposed to delay for 2 seconds, or is it supposed to delay for 32 seconds? So somewhere inside this schedule has to be some kind of state. And in ZIO1, and I think in like the most simple way you would do this, that state would just be hidden somewhere inside the implementation of this, and you wouldn't really have to worry about it. But that creates a little bit of a problem potentially if you want to serialize and deserialize these schedules, and you want to use them within things like Zeo Flow, where we're going to have these different remote nodes, and maybe there's some part of this like schedule how it's supposed to be retrying something that we want to be able to save to disk and load from disk, and we want to be able to keep track of the state of. And so what this state here is it's just one of these type refinements, right? Sometimes it's called the aux pattern, but we've tried to use this with construction before. So if you want to go back, there were a couple of videos we did when we were implementing type level sets and we were doing path dependent types, where you can review a little bit more about what this syntax is doing. But basically, it's just holding on to a little bit more information about what this schedule is. So you'll see if we go to the implementation of the schedule here, it maintains some kind of internal state, and inside it, it has that state. And so at this point, you see the schedule just has the 3 type parameters, but the state is inside it. And the with state lets us hold on to that additional type information if we want to. So because Zeo is a library, if you look at the source code for this, we're trying to preserve that state information whenever we can. And so if you look at all of these constructors, they're all going to return things that tell you exactly what kind of internal state they maintain. But unless you want to do this serialization, deserialization thing yourself, you probably don't need that. And so you can just go back to that more simple type signature of the in, the environment, and the out. but I at least wanted you to see what that was. So if you are looking at the source code, you don't get thrown off by that. All right, let me do a little check-in on questions here, and please tell me if this stuff makes sense. Okay, so we've got a question filling out. So a running schedule is a lazy list of times. So a finite schedule would be S take N. So we'll come back in a sec to the internal representation. So let me maybe hold that question. And then you say it feels like the retryness or repeatness should be part of the respective operators and not the schedule's problem. And yeah, so that's basically what we're saying, because I can take the same schedule, I can take the same schedule.fixed, and I can say retry schedule.fixed 10 seconds or repeat schedule.fixed 10 seconds. I think the only time it becomes relevant is with that input type of if the schedule only works for a certain type of inputs, right? It says, well, look, I want to look at your domain errors, and I want to just do a different thing for different domain errors. Then that schedule is only going to make sense if it's consuming domain errors. So in that case, it's probably only going to make sense if you use it to do retrying versus repeating. Okay, yeah, we want to depend on the failure times, right? So yeah, it's not just a lazy list of times. That's definitely right. Okay, we've been using options, distinguish what to retry and what not to retry. And okay, yeah, we got a question about kind of how we could add some monitoring to it or something. So that's an interesting one we could come back to. And so then there's a question, if out is for keeping the state the schedule uses. And so no, I think you saw that state is for keeping track of the state the schedule uses, and state is invariant. Out is the output of the schedule, which may say something about what the schedule did. It may say, hey world, here's the last time I delayed for. But that's kind of read-only versus, yes, the actual state is read-write and is invariant. And then Naveed asks, is there a reason that particular one is using the kind of this weird option of long, long, long? And the main reason is just that when we're holding on to the state type like this, we do end up exposing a little bit of internal implementation here. And so at least so far, we felt like it hasn't really made sense to kind of create separate data types for the state for each of these individual operators. Right, I mean, we could definitely imagine this being something like fixed schedule, final case class fixed schedule state. And then we could have a more specific representation of this. I think so far we felt like this was relatively low level, that it was really, you wanted to support this specific use case around serialization, deserialization, and in most cases you wouldn't be working directly with the state type, but it's definitely something that you could potentially do. Okay, so how do you combine two schedules that contradict each other, and can that happen? Okay, so I think that's gonna tee us off really well for our next part of our exploration here, which is we're gonna have to, I think now that we understand those type parameters, we're gonna have to look a little bit at like, how do we actually represent a schedule? Like, what is a schedule under the hood? And then I think that will help us think about what types of composition operators make sense. So the way that let me just check one more time. No worries, Phil. It's great. And probably if you had a question about one thing, like other people did too, so it's probably good to review it all now. It's all great. Okay, so a schedule is really defined. These are the only abstract parts of the schedule interface. So a schedule maintains some internal state. We don't know what it is outside of the schedule unless we use that with state thing to expose it. It's actually got an initial value of that state. And then it has this thing that's called a step function. And let's unpack this a little bit because it's not the simplest signature. But so the step function says, give me the current time, give me some input, So this would be the error from the Zeo or the success value, depending on whether we're repeating or retrying. Or maybe it would be maybe it would just be the unit value if this was any and we're using it for something else. And then give me a state. And I will give you back a Zeo workflow that will give you a new state, one of those output values, and this thing called a decision. And if we click through and follow this through, this decision thing is just a sealed trait, and it only has two cases. So the schedule can say, I'm done, which means I don't want to continue anymore, or I'm willing to continue, and here is the next time interval that I'm willing to continue on. And for now, I think I might encourage you, just as we're kind of building up complexity here, to think about this interval as just a specific point in time that represents the earliest point in time the schedule is willing to recur. So, right, hey, I'm willing to recur right now, or I'm willing to recur a second from now, or 10 seconds from now. In fact, it's the representation is actually a specific window of time, because we also want to be able to support more cron job-like functionality, where you might not just say, hey, I'm willing to recur 10 minutes from now, but I'm willing to recur on Wednesday between 9 a.m. and 10 a.m. Pacific. But I think let's start with just the concept of it being a point in time as we build up to this. And so if we have those things, then I think we could start to see how this gives us the tools to solve those challenges we described for ourselves earlier. So we said we wanted the schedule to have enough information to tell us when and how many times to repeat or retry something. And now I think we can see, if we go back to the Zeo schedule data type, which maybe I closed that, I should have, how we could do that. Because let's take retrying. So I'm going to run my Zeo, and it's either going to succeed or it's going to fail. And if it succeeds, I'm done, right? It was successful, I don't need to retry it. If it failed, then it gave me an error. And the error is the input. I can just have Zeo use its clock and get the system time, and I can get the time. So I've got the time, I've got an error, I've got from the schedule an initial state. And so I can put those three things together, and I can run it, and I can get a new state and a decision. And if my decision is done, then that means that my retry schedule is done. And so if I got a failure the last time, my retry schedule is done, then I'm donezo, right? I just have to like fail with the failure I had. I retried it however many times I had to retry, and it still failed. So it is what it is. But if my decision is to continue at some time in the future, then I can sleep until that time in the future. And then I can call this step thing again. And I can call it with the new time in the future. I will retry my workflow at that point. And again, if it succeeds, I'll be done. If it's not, it'll give me a new failure, and I'll feed that new failure in. And I'll have an updated state from the last time I ran this. And I'll just keep doing this over and over again until this thing says it's done. And so that's what it's going to mean to retry or to repeat a schedule. Let me check back in and see how that's. Okay, definitely jump in with a question on that. But that's the overall semantics of what a schedule is. And so once we have this, we can use it to start to implement a bunch of these different schedules. And so let's look at some basic schedule constructors here. And one of the cool things about this is we see how like we can start with some very simple schedules and use them to construct things that end up being pretty useful. So for example, this schedule here, so this is schedule.forever. So this is a schedule that always wants to continue. It doesn't delay at all. So it's just like repeat, 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 repeat forever. And so you might say, well, how is that useful? How are we going to do anything else with that? But then you start to say, okay, well, let's look at this schedule recurs. So if I have a schedule that wants to continue forever, then I can use this while output operator. And this while output operator is just going to say continue as long as that thing is true. So let me go back to that recurs there. Sorry, def recurs. So now this is a schedule that wants to continue a certain number of times. It doesn't care about delays. It just wants to continue 10 times or 100 times. And similarly, we can have something like this schedule.linear. And so the documentation says this is a schedule that always recurs. So it has no limit on how many times it occurs, but it does so on this time interval. And we have lots of other ones. We have like, right, we saw the fixed delay. We have another one called spaced. And all these have like specific semantics of like how these durations work. But so then you have this question that I think it was Phil was going to, where he was saying, okay, well, how do we combine these schedules, and could you have, oh, I think it was Ignacio, sorry, who asked the question of like, can we have schedules that contradict each other? And so I think the answer is that as defined this way, we can't quite have schedules that I would say contradict each other, but we have schedules that say different things, and then we need different semantics for what it means to combine them. So let's try to start doing that and maybe get into like a little bit more actual code here. So let's start by defining a schedule that I'll call 10 times. And so this will be schedule.recurs 10. And so if we look at this, this says a schedule spanning all time, which only wants to recur this many times. This only wants to continue 10 times. And then let's do another one, maybe once per second. And I'll do schedule.fixed 1.second, let's say. And we can look at the documentation, the schedule that recurs on a fixed interval. And this is a schedule that always wants to recur. So let's start playing with these a little bit. So maybe, yeah, we can even use this hello Zymposium. And so I could do repeat. And let's start with the 10 times. And this is schedules. Okay. And so we see it repeated with no delay. Now, one thing to note about this that is a little bit of a watch out I sometimes see people run into, that I just want you to be aware of, is if you count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You'll see you actually saw this printed 11 times. And conceptually, like if you think about it, it makes sense, right? Of like I printed it once and then I repeated it 10 times. So 1 plus 10 is 11. But sometimes people expect when you do the repeat 10, you would only get 10. So just remember the repetition is in addition to the original run when you repeat it, because it needs that output of the first value to feed into the future repetitions. But you can see that I think with that caveat, this had, I think, the expected behavior of it repeated it 10 times. It didn't do it with any delay. Let's try the other one. So let's try repeat once per second. And this is 14. And you'll see I'm getting, at least eyeballing it, roughly this 1 second delay. And I think it's a little hard because my screen is there, but you can see when I highlight that it just keeps going forever. And this schedule.fixed, it has no concept of like how many times it should run. It's just going to keep running over and over again. So in a way, that's good. That in a way, that's good that these are two separate things, that I can kind of define these concepts of how many times and what interval I want to do it on separately. But that says that to actually have this be really useful to me, I need some way to combine these two schedules. Does anyone who's worked with schedule remember what the operator is that we would use in this case? Yeah, so someone says and I think that actually goes to Phil's point, and maybe we'll go back in a sec to the 10 times and 20 times. So you say you don't see operators, but well, they actually are there. So yeah, there are definitely ors and ands, and we'll look at those in fact right now. So yeah, so I would say one of the most useful operators, like if I only had to know one operator for composing my schedules, I think it would probably be this and operator. And so and says create a new schedule that wants to recur as long as both original schedules want to recur. And so let me maybe define another one here. Val 10 times once per second is equal to 10 times and once per second. So let's look at what this looks like. Oops. And so let's maybe kind of build some comfort with this, with thinking about how this gets applied here. So and says when we get an input, we're going to run both of these schedules, and we're going to see what they want to do. And so our rule is basically, let's kind of think about our possibilities. So if we've got like a left and a right, we could have that they're both done. We could have that one's done and the other wants to continue. We could have this one wants to continue, this one's done. Or we could say they both want to continue. So this one's easy, right? If they're both done, we're done. What and says is it only continues as long as both want to continue, right? It's like and, it's only true if both things are true. And so if one is done and the other wants to continue, well, sorry, we're done. And similarly, if it's the other way around, sorry, we're done. And so the only one that's a little bit trickier is we have, let's say they both want to continue, but they both want to continue at different time intervals. And so here we would continue at, basically we can, in our simple mental model where we're thinking of these as specific points in time, we can think of it recurs at later time that these two schedules want to continue. And so let's think about how that would fit into our situation here. So we run this schedule, and the first time this guy says, I want to continue, and I want to continue right now. And this one says, I want to continue, but I don't want to continue until a second from now. So we say, okay, well, we're down here. We're in this part of the world. This right. The left one said they want to continue right now. The right one said they want to continue a second from now. So we're going to do the later of those two. So we're going to continue a second from now. And then we're going to do it again. And the first 10 times, we're going to get the same result here, right? Of this guy is going to say, I want to continue right now. This person's going to say, I want to continue, but I need to take a little bit of a break before I'm really continue. So they'll compromise. They'll agree that they'll continue, but after this one takes a break, and that'll go on for 10 times. But then we're going to get to the 11th time. And then this person here is going to say, I'm done, right? I don't want to continue anymore. I was only supposed to go 10 times. So now I'm done. This one here says, well, I want to continue. I'm happy to continue a second from now. So we're basically in this branch here, but because we're using the and operator, and its semantics are we only continue as long as they both want to continue, we're going to be done. And so the semantics of this are going to be, I think what is kind of implied by the name of this, that we're going to do it 10 times, 1 second delay between them, and then we're going to be done. So let's try running this. So we see we're getting that behavior of 1 second delays. Give that a little bit of time. Into our 10, and we're done. And so I think to go back to that question of like, what do we do with contradictory schedules? I'm not sure they quite contradict each other, but they can definitely contain different information. And the answer is we specify essentially how to handle that with these operators. So the and operator specifies one particular way of handling this information. We can imagine there are other ways, and we can look at operators for those as well. But I would say this is probably, again, if I had to only know like one operator for composing these schedules, I think and would probably be that operator. Okay, so yeah, so after the time, the 10 times is done. That's right. And yeah, okay, so the example of cases covered it. So is the memory footprint constant? Yeah, because each time you run, you just keep track of that new state. So as long as you're constructing that state in a way where it's not like growing, you're not like adding to a list each time, then it would be constant. There are some operators where like if you say, I want to collect all the outputs into a chunk, then we got to build that chunk along the way. And if you repeat it a billion times, you're gonna have a problem. But as long as that's just that state you're maintaining is just like the last delay or something, then it would not grow. Yeah, and so that's exactly right about interval intersection. And so yeah, you can have this more geometric interpretation in terms of interval union and intersection here. So yeah, so and is one very simple way to combine these, and I would say is one of the more useful ones. Let's see if we can look at a couple of others here. So another thing that we might want to do is we could think about running one schedule after another, right? So we might imagine, well, I want to do it 10 times for 1 second each, but then I want to do it with linear back off, or I want to do some delays, and then I want to like do a couple times fast. So one way is you could think of the and as maybe one way of doing kind of parallel composition, right? If you're saying, well, I want to give these schedules both the chance to contribute right now to the decision about what we're doing. But another way you could think of is more sequential, where you let the first schedule do its thing until it's done. And then when it's done, you let the second schedule do its thing. And so that's another way you can build these more complex strategies. And so let's do another one. Let's say val 10 times once per second, and then say 5 times fast. And so this could be 10 times once per second. And I can either use the plus plus or I can use the and then operator for it. Maybe I could do, yeah, schedule recurs 5. So let's try this. I just did a completely different exercise. Let's see. We're parsing some chess moves. So we're getting our 10 repetitions, 1 second each between them. And then maybe, yeah, that was probably not the most exciting thing. But then we get so we got the 11 with the delay, and then we got 5 really fast. And so that's kind of one set of ways we can compose operators. Another way we could do is, maybe I'll call this like debugged. And so let's say I do that whole same thing, but now I could, do, let's say, clock dot nanotime dot debug. So maybe that'll be nicer. We'll be able to see the times for each of these. Let's try this. I'm not sure the nanotime was the most readable. But so we can see here how we had that longer duration, and then these all occur in very short duration succession to each other. And so that's another example of like, so we had binary operators for combining. So we had and, which represents one kind of parallel composition. There's also an or operator that you can use. I would say and I think practically tends to be a little bit more commonly used, but you have both of those, as well as we saw this idea of sequential compositions of schedules. And then we also saw an example of a unary operator here that's going to do something with the output of a schedule. So could like, let's say debug it or log it, or I think someone has a suggestion about like metrics for it, sending that somewhere. So it's another thing you could use that functionality for. If we saw this lets us perform a Zeo workflow for every time a schedule runs and get access to its output. Let me check in again on questions here. Yeah, so Phil asked a very interesting question about like if we're doing the serialization of state, is there an issue with the environment we work with? And so I think that's like a nice thing where like the clock is just a service. So like it's fine if it doesn't. I mean, there needs to be an implementation of the clock service on that other node, but it doesn't need to be the same one for that. Though you would also have to kind of make sure you weren't like relying on something that was only specific to that one node. So I would say that the schedule is not, itself going to solve all of your problems of distributed computing, but is kind of meant to be a building block for to allow things like Zeo Flow to use it as part of what they're doing. Okay. Well, we're actually, I said we were going to go over an hour, and we actually have already gone over. So maybe one other thing I can show you is one of the nice things about these schedules is the motivating use case for them was repeating and retrying Zeo workflows. But as we saw, the schedule itself doesn't really know anything about repeating or retrying. It just knows that it takes some input, and that input could be not meaningful values, right? It could just be the unit value, because the schedule could take any as its input. And so I think what we've started to see more of as we've done more with Zeo and with libraries built on top of Zeo is the schedule data type can have a lot of other uses. And so let me see if I can find a good, I'm just trying to, yeah, so let me see. Yeah, so like here's a nice example of, so I think as we've talked about, Zeo added this support for metrics as part of Zeo Core and Zeo 2. And so one of the things that got added was this concept of a polling metric. And so this is a metric that will poll for something in the background on some schedule. And this is another like nice case where you can use a schedule to describe that. This schedule fork operator, this is actually another like nice example. So this is going to fork a fiber that is going to do something on the background on some schedule. And you can see the implementation is actually pretty simple here. We're using this fork scoped operator, which is just forking it, as forking it in a scope. So when the scope is closed, the fiber will be interrupted. And then we're using one slight variant of the repeat or retry, which is we said the repeat or the retry would always do it that one extra time. If you don't want that one extra time, if you want kind of schedule recurs 10 to do it 10 times and not 11 times, you can use this Zeo.schedule operator. And you'll notice the difference here is that this one doesn't allow the schedule to rely on the input of the output of the workflow. So it's not, this is just like do it 10 times versus repeat it 10 times. So as you look at different Zeo libraries, like Zeo Streams also has some operators with schedules where you could like create a stream from the repetitions of a schedule. And you could use that to then kick off some different workflows that you're doing. So I think another nice thing about it has been it's given us a common language to describe these concepts about some schedules for doing things. Okay, does anyone else have any questions here? Otherwise, I think this may be a decent place to break. There are, I think as you saw, there are a lot of different constructors on schedules. There are a bunch of different ways to combine schedules, but I think if you understand this idea of like every time you run the schedule, it returns one of these two states of either being done or wanting to continue on some interval, and then using that basis of combining them. So either saying, well, I'm going to run them both, and I'm going to have some rule for how I decide what's due based on the results of each of them, or I'm going to run the first one as long as it wants to continue. And when it's done, I'm going to run the second one as long as it wants to continue. And when that's done, I'm really going to be done. I think this will kind of give you what you need to understand all those operators and see how they fit together. We got a couple folks typing, so I'm just going to give folks a minute. Yeah, so Naveed has a question, and I was probably making it sound more complicated than it is when I said working with the Zeo runtime, because it doesn't really need to work with the Zeo runtime. Just like somewhere there needs to be that implementation that basically does the stepping of the schedule, right? That kind of runs the thing once and then steps it and then does it again and so on. And so the way that actually happens, for those who are curious, let me go back to the actual schedule. Oh, not there, sorry. So we found that it was helpful to wrap that logic of actually running it into this thing that we call the driver. So anytime you have a schedule, I can spell it correctly, you can create this, you can call this driver method. And this gives you a interface that you can use to step the schedule. And if we look at this, we can see that, well, first let me go to the driver and let's look at that. So the driver basically has these 4 parts of its interface. So the driver says you can get the state if you want to look at it. It gives you the ability to reset the schedule if you want to say like, okay, I'm done with this schedule, reset it back to its initial state, and I will try running again from there. You can step the schedule by giving it an input, and it's going to give you a new workflow that's either going to fail with none, which is essentially saying the schedule is done, has nothing else, or it's going to give you an output and say it's going to continue. And then you can ask for the last value from the schedule, which there may not be a last value, and then it's going to give you this exception here. And so then what you do, if we go to Zeo, let me see if I can go back here. Oops. Let's look at the implementation of like repeat. So when I want to repeat something, I call that driver to get the schedule driver. And then I just define this loop function that, given, in this case, this is repeating. So this is the successful value of the workflow. So given an output of the workflow, feed it to the driver and see what the result is. And so this case here is where the schedule was done. And so then get the last value. This case here is where the schedule said it wanted to continue. And so then run the original Zeo again. And then if it succeeds, go back to looping and just keep doing it. So the actual, I kind of just, I guess saying runtime just to kind of talk about like the Zeo library overall, but there's actually no special logic that needs to be done in the runtime. It's really just this loop function, and it's pretty straightforward Zeo code that if you wanted to, you could try doing yourself. If you've got the interface of the schedule with its step function, and you've got a Zeo, then you've already got everything you need to write your own method to retry the Zeo or repeat the Zeo with the schedule. And this driver thing and this implementation is just kind of our way of doing it, but it's basically a pretty straightforward like recursive function and error handling. Okay, and yeah, so you hopefully you saw where it lives now, and yeah, it's basically that driver functionality in schedule.scala, which tries to encompass some of it so it can be used in multiple places, and then it would live in those specific methods, so like repeat, retry in Zeo.scala, and there's slightly more advanced variants that let you like do something with the error if there's an error. And then the basic ones are implemented in terms of that, but there are about 3 variants of repeat and retry each. Okay, so I think that is probably good for today. Maybe I'll give 1 more minute if anyone else has questions, but otherwise, hope everyone has a fantastic weekend and is enjoying your summer here.